Hello everybody and welcome back. Cold, snowy outside, horrible out there. Let's snuggle down with the Fourier transform, one of the great bits of mathematics. And we'll plunge straight in with the definition of the Fourier transform. So what we're going to do is we're going to carry on with our idea of taking weighted averages of functions, only this time we're going to take a weight not with an exponential function, a real exponential function, but now with a complex one, in other words, trigonometric functions. So in some sense, we're going to generalize the idea of Fourier series. We'll come back to that a little bit later on. So here's the definition, definition 71. You need an integrable function f, so you can see immediately we're going to be dealing with a different class of functions than we did with the Laplace transform. And then what we do is we multiply f of x by the exponential function e to the minus isx, and we integrate over x. So we do that for each s, and we get a function which we call f hat of s. So notice there's a minus sign here. There are in fact several different definitions of the Fourier transform, all equivalent. Some people put a plus sign here. If you're an engineer, you put a 2 pi in the exponent as well, because you're thinking of s as a real frequency measured in hertz, and you also call I j, which is another matter altogether. And there is also a definition in which there's a 1 over square root of 2 pi in front for normalization purposes. Ignore all of those. We're going to work with this definition, which is in many ways the cleanest and the simplest for what we're going to do. So we look at this and we say, well, f has to be integrable, excuse me, and that means immediately that lots of the functions we used for Laplace transforms, like e to the x, are simply not applicable. You can't take the Fourier transform of e to the x in the same way you can take its Laplace transform, because e to the x is not integrable on the whole real line. So that's one thing we have to note, but we're going to come back to that. And then the second thing to note is you may already have seen this, because if you're doing probability, you can take the characteristic function of a random variable x, by definition the expectation of e to the I tx, it's usually called t, the variable. And then to work out the expectation of any function of x, what do? You multiply by the density and integrate that function, so that you integrate the density times e to the itx. And now compare that definition with this one here, and you see they're the same if you just change minus s up here for t, or alternatively s becomes minus t. So this is the same thing. So many of the things you may have done in probability are in fact just Fourier transform theorems repurposed for that use. So let's have a look at an example and see how it works. This is a collection of examples. Some of them are in the lecture notes, some of them are not. Here's the first one. We just take the function which is 0, goes up to 1, and then comes down to 0 again, the top hat function, and it's 1 between minus a and a, so it's an indicator function, and define 0 if you're bigger than a, 1 if you're less than a in modulus. The Fourier transform is easy to work out because you just have to integrate from minus a to a because the function vanishes outside, e to the minus isx, so you just do the integral, and you end up with 2 sine of as over s, a function which is known as the sinc function in signals processing. Here's another example. We're already breaking our rules because if we take f to be delta of x minus a, delta of x minus a isn't technically an integrable function, but that doesn't stop us. We can use the delta function on a continuous function, and of course in the definition of the Fourier transform here, e to the minus isx is certainly a continuous function, and so we can do the sifting property that when you multiply e to the minus isx by the delta of x minus a, you just get e to the minus ias, because you evaluate by putting x equals to a. Here's another one. This is a useful one. If f is e to the minus a times the modulus of x, so this is a two-sided exponential. It looks kind of like that, goes up and then to a point at the origin and then comes down again. Then its Fourier transform can be worked out by direct integration. You just split the range of integration up into minus infinity to 0 and 0 to infinity. From minus infinity to 0, e to the minus a mod x is equal to e to the a times x, because the modulus of x is minus x when x is negative, and then ax is negative, so you get the exponential decay. Similarly, here's the exponential decay there. You evaluate the integral directly, and you get 2a over s squared plus a squared. Here's another example. If f is a over x squared plus a squared, then f hat is the integral minus infinity to infinity of a over x squared plus a squared e to the minus is x dx. And this one we have to do by contour integration. We don't actually have to do it by contour integration because there's a trick which we will learn later on when we do the Fourier inversion theorem, but for now we have to do this by contour integration. It's a very routine integral. We saw it earlier on when we did the Laplace inversion of 1 over p squared plus 1 to get sine of x. We consider f of z, where z is obviously x plus iy, is a over z squared plus a squared times e to the minus is z. And the key is that what you need to get is to complete your contour, to make a closed contour and use the residue theorem, is you need to get decay of this exponent, not growth, when we close with a semicircular contour, either in the lower half plane or the upper half plane. And if you do a little fiddling around with this, you will find that you need to close with a semicircle in the upper half plane if s is negative, and the lower half plane if s is positive. To see which is which, you just put z is x plus iy in here, and then fish out the real part, and you'll see that that's what you have to do. So you go that way, round anti-clockwise, or you go round anti-clockwise like that. In this case, you pick up 2 pi I times the residue at ia, and in this case, you pick up minus 2 pi I because you're going the wrong way round, times the residue at minus ia. But when you do it, you work out the residues easily enough. There they are. Straightforward ones, because all you have to do is differentiate the denominator here with respect to z, then put z is either ia or minus ia, and you do the arithmetic and you add them up, and what you get is pi e to the as if s is negative, pi e to the minus as if s is positive, which is pi e to the minus a mod s. Now, you might have noticed something here. If you go back to this page, we took the Fourier transform of e to the minus a mod x, and we got 2a over s squared plus a squared. Now, if we take a over x squared plus a squared, we got pi e to the minus a mod s. This isn't a coincidence, and you'll be able to see why in the next lecture. Here's another example. This is the characteristic function of a normal random variable, slightly disguised. If f of x is e to the minus a squared x squared, then its Fourier transform is the integral of e to the minus isx, e to the minus a squared x squared. Complete the square in the exponent, so you've got an x squared there, you've got an x there, and you've got to add something which, as far as x is concerned, is a constant, and that thing that you add is s squared over 4a squared in here, minus s squared over 4a squared outside, so they cancel. Take this one outside. Now make the change of variable x plus is over 2a squared equals u. Now you shouldn't really do that when you're doing a complex integral, because what you're doing is, in effect, you're moving the contour by a distance is over 2a squared. In other words, you're moving it up parallel to the real axis like that. So you shouldn't do that without a justification that says you integrate round a rectangular contour like that, between the two contours, the two lines, and show that the contributions from the ends vanish. And that's done for you in some detail in the lecture notes, so I'm not going to reproduce it here. So anyway, once you've done that, you've got e to the minus s squared over 4a squared, and this is now a standard integral, which is root pi over a by the change of variable au equals v, and then it becomes the integral of e to the minus v squared, which you know is root pi. So that's another example. In fact, the example we had before, I should perhaps go back. This is also a probability distribution. This is a Cauchy probability distribution, a over x squared plus a squared. You need a factor of pi on the bottom to make it integrate to 1, and then you have the Cauchy distribution in probability. Of course, any positive integral function can be made into a probability distribution by dividing by or multiplying by something to make its integral equal to 1. We're going to come back to these examples in the next lecture, so please don't forget them. Now, when we did the Laplace transform, we were able to show a lot of useful properties, and of course it's no surprise that those properties apply to the Fourier transform as well, because you could almost read them off by replacing p for the Laplace transform by minus is for the plus is for the Fourier transform, but it's best to state them. Before we do that, we're just going to note a proposition called the Riemann-Lebesgue lemma, a very famous lemma actually, which says that if you have a continuous function or an integrable function, and you multiply by either cos sx or sine of sx and then integrate over x, then when you let s become very large, the limit is 0. And the reason for this is in the two pictures at the bottom. Here, this smooth curve here is the f, and then here is one of your cos or sine of sx multiplying f, so you get a modulated sine or cosine like that. This is for quite a small value of s, and this is for a larger value of s, where you see we fit many more oscillations in the same distance. Now, remember what an integral is. It's just adding up all the signed areas above and below the axis. And you can see that the narrower these peaks and troughs get, the more that area there above and the next area there below are going to become equal, the closer they're going to become to being equal. And so when you integrate, they're more or less going to cancel. And that's the reason the Riemann-Lebesgue lemma works. With a bit of work, you can show that for most functions, the error is of order 1 over s, so it decays to 0 like 1 over s. If you want a little exercise, prove to yourself that the envelope function here, the f, touches the modulated envelope like that it touches it actually as I've drawn it at the top of the top of the peak, where the sine or cosine has its maximum and minimum for the negative envelope. A little property that you might or might not believe is true, but actually it is. So here we've collected in theorem 80A, called 80A just because it's brought together a number of results from the lecture notes, 6 properties of the Fourier transform. And for all of these, we need the f to be an integral function vanishing at infinity. You'll see why in a minute. It's not the case that all integral functions vanish at infinity. I challenged you to find an example of that in an earlier lecture. And we're going to assume that all the Fourier transforms exist because we're not getting into technicalities here. So 6 things. First, it says that the Fourier transform vanishes at infinity when s is infinite. The second is that the opposite end of the spectrum, the Fourier transform at the origin, is the integral of f, and so it's 1 when f is a probability density function. That's a property of a characteristic function, of course. Then 2 really critical properties. One is that the transform of the derivative f prime, you just multiply the transform of the function by is. F prime hat is is f hat. And then correspondingly, the Fourier transform of xf is I df hat by ds. So you see there's a nice symmetry between these. The derivative multiplied by s multiplied by x, you get the derivative in both cases with a factor of I. Then two results on translation. Also, these two go together. If we multiply our f by e to the iax, which of course doesn't affect the fact that it's integrable, then we get f hat of s minus a. And if we take f of x minus a and take its transform, then we get e to the minus ias f hat of s. So notice there's a minus there and a plus there. So 6 properties. Let's go and prove them in a moment, but first we might note that clearly these two go together, clearly these two go together, and clearly, as I said, all of them correspond to properties of the Laplace transform, but also they are just a bit cleaner, and the real reason for that is that in the Laplace transform we only define functions on the interval 0 to infinity, and that is less natural, as it were, than defining them on the whole real line. Those of you who've done quantum mechanics will see that C and D are very reminiscent of the position and momentum operators in that subject, and that is also no coincidence because a lot of quantum mechanics is essentially Fourier transforms. So let's just prove this. We're not going to do them all. The first one we've already done. It's the Riemann-Lebesgue lemma that the Fourier transform goes to 0 as s goes to plus or minus infinity. For the second one, that f hat of naught is the integral of f, you simply go back to the definition of the Fourier transform and put x equal to 0, so the e to the minus isx becomes 1. Now, the derivative, you integrate by parts, same as we did with Laplace transforms. Transform of the derivative, the integral of f prime, d to the minus isx. Integrate by parts, integrating on the f prime, differentiating the e to the minus isx. So you get f e to the minus isx between minus infinity to infinity. That's why we need f to vanish at infinity. And then minus the integral of f, then a minus is from the minus is in the exponent when we differentiate, and this is is f hat. And for the other one, we'll start with the answer. I df hat by ds is I d by ds of the integral of f e to the minus isx. Differentiating with respect to s brings down a minus ix from the exponent this time, so this is x f hat of s. And you can do the other two. They're simple exercises by a change of variable. Now, we're going to prove a famous result for the Fourier transform, which is the Fourier convolution theorem. We had a convolution theorem for the Laplace transform, which relied on the definition of the Laplace convolution, where you take two functions and evaluate f of t and g of x minus t. In the Laplace case, you integrate it from 0 to x. In the Fourier case, our functions are defined on the whole real line, so we integrate from minus infinity to infinity. So the convolution of two functions, f star g, is a function of x at the integral minus infinity to infinity f of t g of x minus t dt. And this is something you have seen in probability because it is the density of the sum of two independent random variables. If x and y have densities fx and fy, then you put fx here, you put fy there, and this just says you add up the probabilities of all the combinations where f has the value, x has the value t, y has the value x minus t, so x plus y is equal to little x. You add them all up, and that's the density of f of x plus y. They need to be independent, of course, for this multiplication to work. Second point to note is I started by mentioning the Laplace convolution here. You can, in fact, turn a Laplace convolution into this form by saying that our functions are defined on the whole real line, but they have the form f of x times the Heaviside function of x. And then it's a little calculation to do to show that if you have an integral minus infinity to infinity f of x h of x times g of x h g of x minus t h of t, so it would be f of t h of t g of x minus t times h of x minus t, then you end up with the Laplace form of the convolution. So it's not a surprise, there is a convolution theorem for the Fourier transform, and it takes exactly the same form as for Laplace. The Fourier transform of a convolution is the product of the Fourier transforms. F star g hat equals f hat g hat. And the proof is the same idea as the Laplace transform, but in fact it's a little bit easier, technically speaking. We start with f hat g hat, and we'll show that this is the Fourier transform of f star g. So f hat g hat, there's f hat, integral of f of x e to the minus isx. There's g hat, integral of g of y e to the minus isy. Write this as a double integral, so just take this integral over here. Collect together the exponents, so you have e to the minus is times x plus y. Now the key step is that you put x plus y equal to u. So this is, again, a change of variables in which you go from x plus y equals u and then x. You might write this as x plus y equals u, x equals v. The Jacobian of that transformation is 1, and then you put v back as x again, and you end up with the integral here, in which the x plus y here has become a u, y is u minus x, and this x remains unchanged, and the limits are still minus infinity to infinity. Remember, in the Laplace case, we had to fiddle around with the limits here. Now this is easy, because inside here I have the integral of f of x, g of u minus x dx, and that is just f star g of u, and then I have e to the minus isu comes outside like that, and this is therefore the Fourier transform of f star g. So the product of the Fourier transforms is the transform of the convolution. So let's see some examples of this. The first example is the convolution of delta of x minus a and f of x, where f is a continuous function. Already we're breaking our rules because this delta of x minus a isn't an integrable function, but in the spirit of this course, we'll just go ahead and do it. What the integral of the convolution of this? Well, we need to work out delta of x minus a with t, so delta of t minus a. Then we need f of x minus t dt, and of course, what is that? We simply evaluate f of x minus t by putting t equals a, which is where the argument of the delta function vanishes, where the bit inside the brackets of the delta function vanishes. So this is f of x minus a. And that's no surprise, because this is just the shifting property again. Now, what's the Fourier transform of delta of x minus a? It's e to the minus ias by shifting. So the Fourier transform of a convolution f of x minus a, that's this bit here, is e to the minus ias f hat of s. And just to see where that was, we go back a couple of pages, and it was in this theorem here, part f of theorem 80a, the transform of f of x minus a is e to the minus ias f hat of s. Here's another example. Suppose that we have two Cauchy distributions, probability distributions. f of x is a over pi times x squared plus a squared. G of x is b over pi times x squared plus b squared. So both of these functions look kind of, sorry about that, they look kind of like that, but they decay rather slowly at infinity compared with, say, the normal distribution. Anyway, what is the density of a random variable which is the sum of these two? F hat we know is e to the minus a mod s. G hat is e to the minus b mod s. So f hat g hat is e to the minus a plus b mod s. Remember, I chose a and b to be positive to make my life easy. Otherwise, I'd have been fiddling around forever with modulus signs here. No reason not to do that. And therefore, we immediately conclude that the convolution of these two, f and g, the Fourier transform of the convolution is this, so we can invert both sides. The convolution itself must be the function whose Fourier transform is e to the minus a plus b times mod s, and that is another of these Cauchy distributions with parameter a plus b. So you just take a here and replace it with a plus b, so you have a plus b over pi times x squared plus a plus b all squared. Of course, you could have done that by contour integration, but I bet it would have taken a long time. This is undoubtedly much, much slicker. So the sum of two Cauchy random variables is also a Cauchy random variable, a well-known result in probability theory, and actually an example of what's called a Levy stable process, which is a stochastic process that evolves randomly in time such that the distribution after time A and time B is the same, comes from the same parameter with family A plus B. Another example of that is the normal distribution, and in the lecture notes you'll find a calculation that says if you take the convolution of two normal distributions you get another one, and the sum of the variance of a sum is the sum of the variances, which of course is a result you've known for some time. So we're going to end this lecture with a slightly harder example, a slightly more, this example is a little more out there than the ones we've seen so far, but it's really a very interesting example indeed. It's a bit beyond the boundaries of what I would consider fair to be examinable in your exam question, but do pay some attention to it, and if you don't get your head around it first time round, come back and have another look, because it really is very interesting. And the question is, what is delta star delta? Can we make a sense of a convolution of delta of x with itself? So why might this be difficult? Well, the reason it might be difficult is that you can't multiply distributions. You can't multiply delta by delta. So why can't you do that? Well, first of all, think of one of those top hat approximations to the delta function, the function that was 0 everywhere except between minus 1 over n and 1 over n, and its height was 2n. No, n over 2, its height was n over 2. If you multiply that approximation by itself to get something that might be delta of x squared, well, it would still be 0 except on the interval minus 1 over n to 1 over n, but its height would now be n squared over 4. And then you can't take a limit of the integral. So delta squared is unlikely to make any sense, and indeed it is very difficult indeed to build any sort of a theory in which you can multiply delta of x by delta of x. Similarly, if you take the heavy side of x and multiply it by itself, you get the heavy side back again. And if you start trying to apply calculus rules to something that satisfies that, you don't get very far. So you can't multiply distributions, but you can take their convolutions. And although to do this properly requires a little more work than we have had time for, I promise you it is possible, and it is a perfectly sensible thing to do. So asking what delta star delta is a perfectly good question. And then we can extend that a little bit and say, what is delta of x minus a star delta of x minus b? So I'm going to give you 5 answers to that. If you don't believe me after 5 answers, well, I've done my best. You may not like them, of course, but I promise you that they are right. So let's start with an intuitive one. Rigorously speaking, you can drive a coach and horses through this. It's terrible, but it is sort of the intuitive answer. Delta star delta should be the integral of delta of t times delta of x minus t dt, because that's the definition of a convolution. Now, of course, this doesn't make any sense. This should really be an action, because it's got a distribution, delta, in it. And of course, you can't really have an action because actions act on test functions, not on other distributions. But anyway, suppose we were to do that. How would you deal with this? You would say, well, I've got a delta function here, so I'll put t equal to 0 in that one, and that should be the answer. And so you put, it's like evaluating any integral delta of t, g of t, dt. You put t equal to 0 here, g is delta of x minus t, so you get delta of x. So delta star delta equals delta. And then if you do the same thing for the other one, delta of x minus a star delta of x minus b, well, it's going to be an integral looking like this, only it is, of course, a quote integral, not a real integral. Then you evaluate this one at t equals a, and you get delta of x minus a plus b. Or if you like, you evaluate this one by putting t equal to x minus b, and you get the same thing. And of course, rigorously speaking, this is absolutely terrible, but it is the right answer. So here's another example, another answer. Suppose we believe that delta star delta is a distribution. Then we take a test function, and then we work out the action of delta star delta on phi. Well, that should be the same thing as delta of x times the action of delta of x minus t on phi. Remember, this delta star delta is itself an integral, and this inside action is taken over the variable t, and that's the action of delta of x on phi of x, which is, of course, phi of naught, and that says delta star delta is equal to delta. So this is really the same as answer 1, just with a few actions thrown into the mix. All right, maybe you don't like those, I don't blame you. Here's another answer. Remember that a little bit earlier on, we showed how to work out the convolution of two Cauchy distributions. We showed that the convolution of a over pi times x squared plus a squared and b over pi times x squared plus b squared was a plus b over pi times x squared plus a plus b all squared. So let's do that by putting a equal to epsilon, b equal to epsilon. And so the convolution of epsilon over pi times x squared plus epsilon squared with itself is 2 epsilon over pi times x squared plus 2 epsilon all squared. Now let epsilon tend to 0, and we know that this thing tends to delta of x, this thing tends to delta of x, and so does this thing, because they're all the limits of continuous functions with integral of 1, and each of these functions as epsilon tends to 0 when x is non-zero, and tend to infinity when x is equal to 0 and their integrals are 1. These come under question 8 of sheet 1, which shows that you can take any continuous function and whose integral is 1 and extract delta out of it by taking this kind of a limit. So in the limit, delta star delta is equal to delta. And of course I could have used any continuous function. This one I happen to have to hand, but I could have used any probability density function. So now I could say maybe I can interpret delta star delta in terms of probability. What is delta of x? It's the probability density function of a random variable which is equal to 0 with probability 1. So x is equal to 0 with probability 1, and then similarly I have another one, y, which is equal to 0 with probability 1, and therefore each of them has the density delta of x as a distribution, and then the sum is also equal to 0 with probability 1, because both x and y have to be 0, so their sum has to be 0, and therefore the density of x plus y is also delta of x. So delta star delta equals delta. And for my last answer and the last word in this lecture, I use the convolution theorem. I know that the Fourier transform of delta hat of s is 1, because that is just e to the minus isx evaluated at x equals 0. So delta hat of s is equal to 1. The Fourier transform of delta star delta should be delta hat times delta hat, which is 1 times 1, which is 1. And that's the Fourier transform of delta. And therefore delta star delta is equal to delta. As I say, that example is a little bit more tricky than some of the ones we have seen in this lecture. In the next lecture, we're going to continue with the theme of the Fourier transform, and we're going to see the famous Fourier inversion theorem, and this is probably the mathematical highlight of the entire course. So I'll look forward to seeing you then. Bye.